So the second example from 2.2, we're going to analyze power functions. So here's where we're going to start to pick it apart and see when we change one variable, how does it change the graph and shape of the function. Okay. And we're given two functions, so I'll do the first one, which is a is f of x is equal to the cube root of x. And you might look at that and you'll say, well, that's not really a power function, and I will say, you're wrong. It is, because it's x to the first power and we're taking the cube root of it. And so really that is x to the 1/3. Okay? And so let's look at the graph of that real quick. If I graph this on my calculator, the reason Mr. Adams is showing you how to convert these these square roots with the indices and the powers is because there isn't an easy way to do the cube root of something. I mean, there is a command and you have to go to the catalog, but it's so many steps and it's just quicker to do it like this. So I'm going to graph x to the 1/3, hit graph, and that's what it looks like. So the shape of this thing looks like this. Alright? Now one thing I want to remind you guys is that if we're thinking of this in the terms of f of x is equal to k times x raised to the a, notice again that a is trapped between 0 and 1. 1/3 is a fraction basically. Okay? And what we're trying to do is it says state the constant of variation of the function, graph it, and analyze it. Well, the constant of the variation is simply going to be this term k. Well, we don't write it down, but isn't there a 1 right here? So my constant of variation is k equals 1. Now, like I said before, and I'm going to go into a standard zoom so you guys could see this, k just vertically stretches or shrinks the graph. So if I change k to like 1/2, so if I come in here, see how tall that graph is? Everybody look at the screen. See how tall that is? If I come in and I insert 0.5. In other words, I make k a smaller number. Watch what happens to the graph. Do you see what I did there? It shrunk the graph, vertically speaking. Now, if I come back in here and I change that to 15, watch what it does. You probably won't even see it on the screen. Yeah, I got to zoom out. So let me change that. Let's just make that 5. Yeah, we'll delete that one. Make it 5. And then see how it changes it, vertically stretches it or shrinks it. That's what the constant of variation does. Okay? Any questions on that one? So we're almost done. We got part B. So now here's a weird one. For part B, so I'm going to go to part B. Part B, they want us to analyze g of x, which is equal to 1 over x squared. But I want to write it like this. I want it to look like g of x equals k x raised to some power. And I want to put something up here. How do I do that? What do I put up there? Does anybody remember? Yep, -2, right? Now where that comes from is if I multiply this by x to the -2 over x to the -2, remember this from your Algebra 2 days? These will become x to the -2 all over x to the 2 minus 2, which is equal to, let me get my calculator out of the way, x to the -2 over x to the 0, which is the same as x to the -2 over 1, which is just plain old x to the -2. You guys remember that from your exponent days? Algebra 2, probably even pre-algebra is when they started doing that. So what is k then? So this, I still have to figure out k. So if I read this right, it's just 1 times x to the negative 2. So what's my constant of variation? Well, remember, the constant of variation is k, so we would say k is equal to 1, which is my constant of variation, right? So here's my constant of variation, which is 1, and that just shrinks or stretches it. Next, we were asked to graph it, so I'm going to come in here and I got to turn my calculator on. And we're going to clear this out, and I'm just going to say x raised to the, and then in parentheses I'm going to put negative 2. And that's what it looks like. Now if I wanted to verify that, didn't we say that's the same as 1 divided by x squared? So if I hit graph, I should have the same graph twice, right? And I do. So it graphs like this. Okay. Can you guys see the pink? Looks real pretty on my paper, but I don't know if you guys could see it on the screen. Alright, that's what it graphs like. Then your textbook goes on to talk about domain and range. I suppose we should probably talk about that. So let's go back to A. What is the domain of this graph? Now remember, domain is all the possible x values, right? So what are all the possible x values looking at this graph? Are there any restrictions? No. So the domain is all real numbers, right? What about the range? Are there any restrictions in the y values? Yeah, it looks like it, right? Like it looks like there's a vertical asymptote. So what is the vertical asymptotes? In other words, it looks like it doesn't go any bigger or smaller than a certain number. So let's plug that bad boy back in. So I'm just going to mute these from the display real quick, and I'll plug that in here. So I'm going to say x raised to the 1 divided by 3, and let's graph that. So now if I hit trace and I go along the line here, what does that look like y is approaching? We might say 2, we might say 3, but does it look like there's any restriction? It doesn't grow very fast, but does it look like it would stop? Well, let's look at it this way. If I could plug in any number for x, that means I could plug in infinity for x, right? I could plug in 10 million for x. So what would the corresponding y value be? Well, let's just see. What is 10 million? Well, I'll just put a bunch of numbers. Let's put that really big number and raise it to the 1/3 power. Do you think I'll get an answer? It's a pretty big number. Oh yeah, it's 480.7498566 cubed, right? Do you guys understand what I'm doing here? If I take this, if I take my answer, whoops. If I just take my answer and cube it, I'll get what I started with, right? You guys understand that? Okay, so what's the range then? Is there a restriction on the range if there's no restriction on the domain? No, it shows that I could go up to 480. I've got to put a really big x value in there to get there, but I think it's all real numbers, right? Okay, let's look at the other graph. Okay. When did we say we would have problems with our domain? When do we have problems with domains, you guys? Does anybody know? Yeah, well, we can't take a negative of a square root, and what's the other one? There's a second one, the other popular one. 0 on the bottom. Does this have a bottom? So can I have 0 here? So basically this is all real numbers except x cannot equal 0, right? So the way that we write that is we go from negative infinity to 0, union 0 to positive infinity. What about the range? Well, as this gets bigger and bigger and bigger and bigger and bigger, what happens to the graph? Think of it like this. As I approach infinity in the x direction, I really get like 1 over infinity. And do you guys remember what Mr. Adams said 1 over infinity approaches? Think of a pizza. That's 1 over 2, right? If I cut it this way, I've got 1 over 4. If I cut those halves in halves, I've got 1 over 8. How big is my slice of pizza when I get to 1 over infinity? It's 0. And notice the graph, the y value gets close to 0, but it never actually gets to be 0. So our range is just going to be from 0 to positive infinity, right? Does that make sense? Okay, that's example number 2. Any questions?